All right, welcome to lesson 6.1 notes. We're starting a new chapter here. Chapter 6, all on exponential and logarithmic functions. So, a couple different looks for us here, things we haven't really touched on a ton this year. Logarithms, definitely something new for, I'm assuming, most people. Um, so, we'll do a little bit of everything, graphing them, solving equations, both exponential and logarithmic, and then writing, doing transformations on the graphs, all that stuff. So it's kind of a traditional chapter here. Today specifically, like I said, 6.1 exponential growth and decay functions. Um, we're going to hit all that stuff. So we'll graph them, domain and range. And then look at a couple different models on those exponential growth and decay functions and how they could potentially apply to some real life situations. So without delay, here we go. Exponential growth. So just first, there's a lot here. Let's back up a little bit, kind of at least take some of this away here. So at the heart of it, exponential function, fairly basic, y equals ab to the x. A1, just so some of this stuff is just like formality stuff where a is not going to be equal to 0, right? That would kind of kill this whole function. B, we call the base. It's kind of nice, starts the same letter. It's going to be a positive number for the base other than 1. Okay, and so there's basically two scenarios here that B being greater than 1 is going to cause is what we're going to call an exponential growth function. So what we'd look at a lot of times if we're trying to decide is something a growth or a decay, what's the base of your power? Oh, it's a positive. It's greater than 1. It's, 5 or 2 or 4/3, stuff like that. And then we call that the growth factor. Okay. All right, so taking kind of the a out of it right now, just basically, setting a equal to 1. All right, if a was 1, it would kind of make it go away. 1 times b to the x. So this is our parent function here. Let's look at just some of the features of a graph. It's hard because if we looked at when we did this exact same thing, and I don't want to go too off topic, but when we did things like this, y equals x squared, and we said, hey, that's the parent function for a quadratic function, what does it look like? So say, hey, just pick numbers, plug in a 0, square it, plug in a 1, square it, plug in a 2, square it, and then you were getting outputs for everything. It's maybe tougher here because we're trying to keep it relatively generic. You've got like 3 unknowns here, a y, a b, and an x. Right, so this function y equals b to the x applies to any base that's greater than 1. So there's still some nice points. I mean, I guess you don't have to get too wrapped up in that. But here's our shape, our exponential growth function, where if I plug in a 0 and I take anything to the 0 power, we're going to get 1, right? Anything to the 0 power is 1. So that actually shows up as that's the one nice point we can get on our graph here. But everything else, if I was making a table, I plug in a 0, I'm going to get 1. If I plug in a 1 right here, I'm going to get b to the first power, which is b. So whatever that base is, plug in a 2, b squared. So the numbers are going to shoot up really quick. If you've heard of growing exponentially, that's usually something that grows like super quickly. So that's starting here. That's how that graph would go. It's b squared, b to the third power, b to the fourth power. Holy cow, getting super steep. And then going the other way, if I start plugging in negative numbers, b to the negative first power, hopefully we recall those properties of exponents. That's actually, it's not a negative output. It's going to bring my b to the denominator, 1 over b. If I plug in a negative 2, 1 over b to the second power. So we're actually never getting a negative output. You could plug in a really small negative 50. It's just going to put b down in the denominator and take it to the 50th power. Now that's really small. 1 over a really big number ends up being a really small number. So you can see by the shape of the graph that it's getting really, 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 really close to this x-axis, like minuscule 0.0000000 but it's going to be bigger than 0. Okay, so we end up with what's called an asymptote. We saw these a little bit with our trigonometry graphs or trigonometric functions, but an asymptote, just as a refresher, it's a line that we approach, but we never actually get to. So our x-axis is that asymptote here. Domain-wise, just seeing the graph. Remember, we're thinking left to right. What's the furthest left this graph goes? Forever. There's not a number that we couldn't plug in and take a base to a power, and then same thing to the right. We're going to the right forever as well. So we've got a negative infinity to infinity, all real numbers domain. Range-wise, there is a restriction just by the nature of the function. We talked about it quite a bit, that we're never going to get to that 0. So output-wise, 0 is kind of the threshold, but I'm using a parenthesis, notice, instead of a bracket, because we never actually get there. 0 is never going to happen, so I don't want to include that as part of the range. But basically, anything above 0 is okay, right? If I look down to up, this is going to go up forever, so all the way up to positive infinity. All right, so there's some of the basics. Exponential growth function. Let's just hammer out the exponential decay notes. It follows exactly, nothing's really changing. Look at our, so I'm talking here, what's the parent function is y equals b to the x. Well, what? That was the same as the last one. The only difference between growth versus decay is that with decay, our b at the base of this power is going to be between 0 and 1. It's a positive number between 0 and 1. So we're talking 1/2, 2/3, 3/4, fractional. It could be decimals, 0.6, stuff like that. That's what's going to create a decay, an exponential decay function. Okay. So our table really doesn't look much different. It's not going to look any different, actually. If I plug in a 0, I'm going to get a 1 output. If I plug in a 1, I'm going to get b. I'm going to plug in a 2, I'm going to get b squared. So you say, well, how can this possibly be different? Let's just look at just even a mini example using like 1/4 as my base. When I start taking this to powers, when I take that to the first power, I get 1/4. But when I take that to the second power, and I'm just using 1/4 as like an example that we can hopefully relate to, that's 1/16. We're getting smaller actually as we plug in bigger and bigger exponents, right? To the third power, 1/4 to the third power ends up being 1 over 64. Like, these are getting smaller. 1/2's not like bad, half the pizza, but now we're talking a 16th of a pizza, a 64th. So you're actually getting smaller as we go to the right. What happens if I go the other direction? 1/4 to the negative first power. That, remember, is going to flip it. That's going to bring the 4 upstairs. So that actually, now we're going the other way. We're getting bigger as I move to the left. If I plug in a -2, that's not only going to bring the 4 upstairs, it's also going to square it. So 16 over 1. Yeah, so there we have it. That's just kind of the why behind it. Like I said, our table is not going to be any different. 1 over b squared. It's just by the nature of that base being between 0 and 1, we get kind of an opposite effect going on here. Okay. So again, we don't have to get too hung up on that. For the most part, when we're making our graphs, which we're about to do, we're going to keep things pretty simple here in this first lesson. We're not going to do any transformations as far as vertical stretching and shrinking, or even translating left, right, up, down, or reflection. So we're going to keep it really simple here in these first couple, and hopefully just getting comfortable. I didn't say anything here about domain and range, but hopefully you can tell by the graph, domain would be unchanged, left and right forever. So negative infinity to infinity. And we still have that same asymptote here on the x-axis. So we have that same restriction on our range that we're only going to be above 0. So, all right, cool. Hopefully that makes sense. Just some of the basics. We'll make a couple. We'll do a growth and a decay. They're pretty related as far as the bases go, but maybe it's a good way to illustrate what's going on there. And then we'll move on. We'll look at some models here. All right. Keep her moving. All right, graphing exponential growth and decay functions. So the first part, it's asking us tell whether each function represents exponential growth or exponential decay. So that's we talked about. It's purely just looking at the base. This 2 right here on my power. Is it a number greater than 1, or is it between 0 and 1? And we all know that that's greater than 1. So I would say this is growth, exponential growth. Why? Because the b is greater than 1. Beyond that, this one, like I said, not terrible. Like as far as plugging numbers in, we hopefully know 2 to our different powers. I'll talk you through my approach. I would usually start with whatever is going to make my exponent 0. So in this case, 0 is that number. If I plug in a 0 there, I take 2 to the 0 power and I get 1. And I kind of just go up from there. So, okay, go up to 1. 2 to the first power is 2. Great. Plug in a 2. 2 to the second power, 4. And I usually just go until I run out of table. Or until I run out of graph. So like 2, 4 is still going to fit on this graph. Let's plug in a 3. Plug 2 to the third power is 8. Now my window's starting to get filled up. Okay, so if I plot these points 0, 1, 1, 2, 2, 1, 2, 3, 4, this 3, 8 is going to put us just slightly off. So there's no reason to plug any more points to the right of that, right? We're off the graph. So I go back and say, all right, well, where did I start? I started right here. I'm going to move to the left of that. So the next number to the left of that would be -1. So I plug in a -1, 2 to the negative first power. Remember, is it going to move it downstairs? So it's really 1 over 2, or 1/2, 0.5. If I plug in a -2, so I kind of have to extend my table. I give you room for 4 there usually. I'm sorry, for 5 points, but sometimes you can get by with 3, 4, 5 points. Sometimes it's 5, 6, 7, 8 points. It just kind of depends on how what the base is. All right, I plug in a -2. That's going to move it downstairs and square it. So I'm going to get 1/4 or 0.25. Maybe it's better to see it as a decimal. I think almost at that point we're almost, it's indiscernible the difference between 0.25 if I plugged in a 3. 1 over 8 is 0.125 as a decimal. These numbers start to get hard to plot, right? So if I go -1, yeah, -1/2, I think I can eyeball that in the middle. But now -2, 0.25, we're getting down here. -3, like how much further do I have to go? We're just barely above that x-axis. And we said that was one of the main features of an exponential growth or decay function, is one of the ends of it, whether it's growth or decay, is going to like get infinitely close to that x-axis. So it makes sense that our graph, kind of just gets so close that it looks like it's right on top of it. So you notice when I was kind of talking there, I added my curve, smooth curve, hit your points. Make sure on this left side, this would be an example of a bad graph that I came in and I did something like that, because I've said it now again, the feature, one of the big features, is that this graph does not cross the x-axis. So for now, domain is unchanged. We're talking same as our parent function, left and right forever, and we're staying above that x-axis, so that leaves us 0 to infinity for our range. All right, so we did them all. I should have read the directions better. Then graph the function, state the domain and range. We got it. All right, 1b, guessing we're probably going to get a decay, and I think we do. So the question's the same, tell whether we're exponential growth or decay. I can tell you for a fact, without seeing a graph, that this is decay, because my b is between 0 and 1, 1/2. So these numbers will look familiar. We just saw them pretty much on the last graph we made. The difference here is, well, the first one's the same. If I plug in a 0 for x, anything to the 0 power is 1. And I start going up from here. All right, 1/2 to the first power is 1/2, or 0.5, 5/10. I go one more. I'm getting 1/2 squared. That's 1/4. There's that 0.25. So again, if I'm going left to right, 0, 1, 1.5, and then 2.25. We're down there, right? We know it's going to keep approaching left to right, that x-axis. So if I want to leave that 0.125 off there, I can. Let's go the other way though. All right. So if I plug in a -1, now all of a sudden that 2 comes to the numerator. 1/2 to the negative first power is actually 2, positive 2, right? We're not going negative. -1, 2. Let's put them on there maybe as we go. I plug in a -2. That's going to bring my 2 to the numerator and square it. So we're talking 4 here. -2, 1, 2, 3, 4. And then we're going to see the same number, that last one. Bring the 2 up, cube it. We're going to get positive 8. So we end up with a left to right graph, infinitely getting close to this x-axis, but never quite getting there. So there's our decay domain, second straight time, and then range. Kind of nice to have one there, at least when we're first kind of getting used to it, where that's not really changing. There's not any restrictions there. All right, cool. All right, let's expand. We're still talking exponential functions. What we're going to call here in our next kind of notes section, exponential models. So we have a growth model and we have a decay model. So you can set that up heading, you just kind of left and right, 2 sections here. And if we kind of take a step back and look at them, there's not a whole lot of difference. Y equals a times the quantity 1 plus r to the t, or y equals a times the quantity 1 minus r to the t. All right, so what's the deal here? For basically, we're going to use these in situations where something is, a quantity, whether it's a population, an investment, money, or even just some quantity, even just like I guess I said population, like I was thinking like an animal population, something like that, where something's growing at the same percentage every year. Like, hey, our business maybe is increasing our profits by 2% every year, something like that. That would be an instance of where there's a fixed percent by which we're growing or maybe decreasing by. Maybe the population of a certain species of animal is every year is declining by 5%, something like that. That's when we're going to use our models. And if the population's growing, or if our investment is growing, getting bigger, it's going up by some percentage every year, we'll use the growth model. If it's declining, we'll use the decay model. So what does all this stuff stand for? It's the same in both models. Y says it right here. It's how much exists, how much quantity is left after t years. So t is time in years. That's how much is left. And then what are these other numbers here? A, that's our initial amount. Well, how much did we start with? I invested $5,000 and it grew at 2% every year. Okay, well, that's my initial investment, my initial amount. Or the population was, a certain amount of people or animals or whatever we're talking about, bacteria. And R is the rate. The one thing with the R, is the percent increase or decrease. We just got to make sure that we're using R as a decimal. So everybody better know that when I see 1.4%, like, written out as a percentage, that as a decimal means 0.014. Okay, so we'll have to convert our percentages to decimals. But other than that, that's kind of it. Okay, so we'll look at same thing. We'll look at both a growth and a decay situation. I think maybe not, but maybe just some different ways to kind of look at how we might apply some of these models. Okay, let's do it. All right. So if I read it here, got to do a better job of that. The value of a car in thousands of dollars can be approximated by this model. So this actually just kind of gives me the model. Y equals 25 times 0.85 to the t power. What does it tell us? Y is the value in thousands of dollars, and t is the number of years since the car was brand new. Okay. So the first thing, tell whether the model represents exponential growth or exponential decay. So that actually hasn't changed, right? If I look at the base of the power, what's the power here? 0.85 to the t power. This 0.85, that's a number between 0 and 1. So this first part of What is the model? I'll just maybe answer them down here. I run out of space. Is this model growth or decay? This is decay. For the same reason that the last graph we made was. Why? Because the b, the base of the power, is between 0 and 1. Before we just kind of jump in and answer B here, I want to make sure we're all on the same page here. What's going on here? So like, if I were to start plugging in numbers here, let's just say for the sake of this that, because I want to make sure that everybody understands what does this mean? If let's say I plug in a 1 right there, and and I hammer away on the old calculator, 25 times 0.85 to the first power, which is just 0.85. My calculator returns to me 21.25. What does that mean? So what that means is, after 1 year, the value of my car was $21,250, or maybe the better way to say that would be $21,250. If I move the decimal point over a couple places, 3 places for 1,000 there. I think maybe we should have started with, well, what about this one? If I plug in 25 times 0.85 to the 0 power, my calculator I didn't use my calculator. It stays at 25. What? How can that be? What's going on there? Again, what does that mean? It means that 25, the initial value of my car was $25,000. So it's kind of important just when I see the model to see what is this 25 that's out front. Remember, we just said a second ago that A value is your initial amount or your initial value. So when I see 25 there, that means when I bought the car brand new, it was worth $25,000 after 0 years. Okay. So I just kind of breaking it apart a little bit for us, which leads then to this next for part B then, when it's asking us, okay, well, identify the annual percent increase or decrease in the value of the car. Well, we already said it was a decay, so we're definitely decreasing. Kind of slide here a little bit to get some room. So we are decreasing. It's a decrease by what percent? And we got to be careful here. We're not decreasing by 85%. This model, before I did any subtraction, must have been this. Y equals 25 times the quantity 1 minus what? And then it's been simplified to read as is 25 times point. So I just did the 1 minus 0.15, and that's where the 0.85 is coming from. So when I see this, though, remember, going back to our model, that R, what we just subtracted, that 0.15 is actually, that is the percent decrease in the value of the car. So basically, to put it maybe in words or just to phrase it a way that makes more sense, we're losing our car that we bought 15% of its value every single year. It's decreasing by. Okay, again, that number wasn't on the page. It wasn't a percentage, but it is decreasing. I can tell because it's a decay function. And where did it come from? 1 minus this number tells me my percent increase or decrease. Last thing before we finish up with C here, the other way to think about this is, instead of losing value, or it's still losing value, so I guess that's not going to change, but I guess the optimist way might be to look at this as, well, yeah, you're losing 15% of your value every year, but you are maintaining 85% of your value. So maybe hearing it that way is like, oh yeah, you're right. That's not a bad thing. But anyways, the last one, it's asking us estimate when will the value of the car be $8,000. So it's not saying like plug in $8,000 or anything like that. I don't think anybody would do that. But at this point, for what we know, so I'm kind of scrolling down. I can still see my model right here. When it's asking us to estimate, it's literally asking us to estimate. Like, we don't have a very scientific way of calculating. We're being asked to basically solve for t. What value of t makes this true? So unfortunately, the best option I'm going to give you right now is just kind of to guess and check a little bit. We just looked at a couple, right? Brand new was 25 grand. 1 year we were down to 20. It's worth about $21,000. So, and I know you can't see me, but I'm on my calculator here. I'm going to get. Just going to check. Let's see. In 5 years, let's see what my car is worth. So this is what I'd ask you to just show me. Like, okay, I kind of picked a number there, 5, and I'm going to go 25 times 0.85 to the 5th power, because that's how you would enter 5 years later. My calculator says, remember, it says 11.092, but hopefully we know it means move the decimal point over 3 places, because we were talking thousands of dollars. It's actually 0.93. So that's the value of my car in 5 years. Didn't quite hit that 8,000 mark, so I don't like that one. We got to keep going right in this direction. So let's go maybe to 7 years, just to kind of see where we end up. So I'm going to keep that exact same input, except switch my 5 to a 7 and just say, okay, 7 years later, what's my car worth? Calculator spits back 8.014. So that I kind of like. $8,014 ish area. I know there's some cents and stuff in there, but that's pretty darn close. I mean, we could look at 6, but 6 is going to take us, or I'm sorry, we probably go the other way, go to 8. After 8 years, you could look at 6 too. After 8 years, my car is going to be worth less than this. It's worth about $6,812. So just slightly after 7 years, my car reaches that value of about 8,000. So not that one. That's the one we want. So we'd say, to answer the question about when, after about how many years, I'd say about 7 years, my car hits that value of about 8,000. Whoops, 7 years. All right. So that was the last part. Just kind of use the model a little bit to kind of guess and check. All right, let's take a look. Slightly different here, so it's not exactly the same kind of setup or situation here. But there's our first example with one of these exponential models. So now you can see the heading. It's asking us, we're going to write one. We're going to go back here and say, okay, a growth or decay model. We'll start maybe with the generic one. We're going to get a rate, an initial amount, a time. So let's see here. Information-wise, in the year 2000, a while ago, the world's population was 6.09 billion. Wow. During the next 13 years, the world population increased by about 1.18% each year. So we talked about that when we did the models, that this is the situation when something's growing, increased, there's a good word for us, increasing by about 1.18% each year. That right there, that word increase, tells me this is a growth model, right? We're growing. Okay, so for part A, it's asking us to write an exponential, there we go, a growth model that models this situation. It gives the population T years after the year 2000. Okay, so generically, we'd start with the model with y equals, remember, A is the next thing. What's my initial amount? So in the year 2000, that's when this model is supposed to be based on, the year 2000. So in the year 2000, our initial amount was 6.09 billion people. All right. And then we're going to add, it's always 1 plus my growth rate. It says we're growing by 1.18%. So remember, this is the percentage increase, but as a decimal. So I need to move that decimal point over 2 places, 0.0118 to the t power. So the only thing I would ask you to do here for part A is just simplify this. I wanted us to see, like, where is this coming from? So 6.09, there's really not a whole lot to simplify other than 1 plus, 0.0118. So that right there is going to serve as our model. That's going to give us our population T years after the year 2000. And then to finish part A, it says estimate the world population in 2005. So the follow-up then is, all right, well, you now this model that you just came up with, let's use it. In the year 2005, what was the population of the world? So what are we going to do? We're going to use the model, say 6.09 billion. We'll just remember to tack that on the end. 1.0118, and then now it's giving us a t-value of 2005, but that's years since or years after 2000, so we should just plug in a 5 there. So what are we talking? How many people here? Going for the calculator, 6.09. I can just do it just like that. My answer will just be in billions, times 1.0118 to the 5th power. If we round and kind of keep it to that nearest hundredth there, about 6.46 billion people would be our population. All right. Part B is very similar to the last example in that it's kind of flipping the question on us here and saying, all right, well, you got your model there. Use it to kind of estimate, to guess and check your way to, what are we saying, about 7 billion. So this is maybe harder to tell. I guess, I don't know. We already said 5 years. After 5 years, we're talking 6.46. So I'm not going to check 1, 2, 3, or 4 or 5 again. Let's start with 7. I don't know. I'm kind of going, I don't know the answer to this right here. So let's check, what is the population after 7 years? We can kind of set it up the same way. I'm sticking with my model. I'm going to just, on my calculator, just go back and switch my 5 to a 7 and say, oh, that's 6.61 billion people. We got a ways to go here. We're trying to get to 7 billion, right? So I don't know. Should we go up to 9 years? Let's try it out. Checking this out here. 6.77. So we're getting closer. I don't know. Maybe we should jump a little bit more. I kind of jumped by 2s there. Maybe let's go up to 12 years later. And this isn't like a scripted thing. I'm trying to figure this out. I'm guessing and checking. And it's hard because, well, let's see. So I plugged in it. I'm kind of talking as I'm doing my calculations there. I'm plugging in a 12 here for T. And now my calculator says 7.01, which I like that. I think that's a pretty good, that's really darn close. I'd be comfortable saying, hey, that's, 7.01 billion people. That's about as close as I think we're going to get with whole years. Now, what does this 12 mean? 12 years, what? After 2000. So, like, to answer the question, estimate the year when the world's population hit 7 billion. We'd say in about 2012, right? So 12 years later from when our model was, applicable. All right. There we go. The last thing we need here, as far as just exponential growth and decay functions, is compound interest. All right. Here we go. Compound interest. So just a very brief, this isn't a personal finance class, but compound interest, first off, what is interest? Interest is money that you make, or the bank pays you for keeping your money there and allowing them to loan it to other people and use your money. So most banks or institutions will give you what's called interest. Okay, and they'll put it right back. They don't have to do anything. They just say, hey, we're gonna pay you for letting us use your money. We'll give you like a 2% interest rate or a 1%, and every so often we'll figure out what your interest is and we'll put it back into your account. So compound interest is where they calculate, basically whenever they compound your interest, that's when they figure out, like, oh, okay, hey, this is one of those times where it's time to figure out your interest. We'll put it back in your account. Your initial investment is called your principal. That's like a financial term. Yeah, and then usually, like I said, they're going to give us some percent, an annual percent. It's like, so this year you're earning 2% interest rate. Here's the thing, though. I said it a second ago. When they compound my interest, that's when that's the the time that they figure out, like, hey, this is a good time to figure out your interest. And that's going to be usually more than just once a year. So we have to account for that, basically. This model, it's a growth model. We're going to use a growth model for compound interest, but it needs to be a little bit more, we need to account for that compounding. So we have a compound interest formula, go figure. It looks very similar to our growth one. We've basically replaced our A, it's still our initial amount, our initial investment. We're just calling it P for principal in kind of this financial world here. A is the amount in the account. After T years, T is still years. R is still your interest rate as a percentage. I'm sorry, as the percentage that's been converted as a decimal. This new thing that shows up here, the only really difference is this N. What the heck's going on? And N is, you can see it right here, it's the number of times per year that they're going to say, hey, let's calculate your interest here. So different ways they could do it. Some banks will say, hey, every month, we're going to figure out how much interest you've earned, and then we'll calculate it and we'll put it back into your account. They could do that every week. So again, per year, we're talking, if they're doing that 12 times a year. Your N would equal, let's just put it on the bottom here. If they're doing monthly, N would equal 12. If they were doing it weekly, every week, maybe every Sunday, they say, hey, let's calculate your interest. So 52 times a year, they're doing that. Daily, 365 times a year. And then, annually would just be like, hey, just end of the year, we figure out, hey, this is how much interest you got. And quarterly would be like once every 3 months, so 4 times a year. Obviously, well, maybe not obviously, but the more they calculate my interest, the better it is for me. If I put $500 into account and they figure out my interest every day and then re-put it back into my account, that's gonna be a little bit better than if they just did it once a year, because my account sits at that 500 all year long until the last day of the year, and they say, all right, let's figure out your interest and we'll put it in there. Whereas here, after day one, they say, hey, let's figure out your interest, we'll put it back in there. It's probably like a half a cent or less than that, depending on how much money I have in there. But they put it back in. And then the next day they say, all right, well, your account's a little bit bigger, so your interest is going to be a little bit bigger. And they put it back in. And then so that's kind of how that works without getting crazy detailed. So I guess, long story short, we got to figure out how to use this formula here. Let's practice it with some actual, values for A, P, or for P, R, T, and N. So we look here. It's telling us we're going to invest. We're going to deposit. Let's just get the formula so we can see it. P times 1 plus R over N to the N times T power. Okay, so everything here, we have basically everything on the right side of the equation here. Our P is our initial investment, so $9,000. 1 plus, that's just kind of the growth component of it. Our interest rate, it's not a great interest rate, if you're wondering, 1.46%. So as a decimal, I slide my decimal point over 2 places, 0.0146. We'll do the N at the end here. So then the T, our T value, how long? We're leaving it in there for 3 years. But then here's the compounded part of it, that they're going to figure out my interest. It's not great, but they're going to do it quarterly, so 4 times every year. And how that shows up here is right here. That interest rate basically gets divided, spread out 4 different times, but then instead of just compound my interest 3 times, they're going to do it 4 times 3 times, or 12 total times throughout the course of these 3 years. So we kind of account for it in both spots there. The interest rate gets split up 4 ways. Say, all right, well, we can't give you that percent 12 different times, but we'll split it up 4 ways, and then we'll account for it with a higher power here. So I guess, short of just taking care of your order of operations here on the right side of the equation, which I have to do, I'm going to get my calculator out. We just got to crunch this and make sure we can do it. So I would type in 9,000. You can do it on a single line as long as you take care of things, times, get a parenthesis going. I want to do all this and make sure that the parenthesis gets done first. 1 plus 0.0146 divided by 4. Let's close up those parentheses. This is one I would probably just leave as 12 or do as, we all know hopefully 4 times 3 is 12. So to the 12th power. If it was a bigger calculation, you'd want to use parentheses around your exponent as well. So I do this and I say, hey, I'm a millionaire overnight. And I say, oh, not really. After 3 years of this money sitting there without me adding anything else or taking anything out, the bank, I mean, it's something. The bank, I'm sitting on $9,402.21. So I've made $402.21 over the last 3 years just for leaving my money there. So like I said, it's something. They've loaned that money out to other people. They're not just some big vault in the back where they threw my money in. They're using it. So they say, hey, we'll compensate you for allowing us to use your money and being a customer here. So yeah, you're not going to get rich. You're not going to go from $9,000 to $50,000 just on interest. So if you don't know much about it and you're getting these, maybe you got a big number here or something happened with your calculation. So just go back and make sure we can get that number. All right, there we go. There's lesson 6.1. We did it all. We graphed. Seems like forever ago, doesn't it? We graphed those and did the domain and range, growth and decay. And then the second half of the lesson was all kind of looking at these real life situations with the growth or decay models. That compound interest kind of just factored into a specific type of growth model. So that's it. We'll call it 6.1 done. I'll see you in future lessons.